Is 1 belongs to this set? 1 belongs to the real numbers except 0. Right? So the 1 which is the identity now is belongs to the set given also, which is a real number except 0. And now we go to the inverse. Let the inverse be A inverse. So when the A inverse is the inverse, so we will have A multiply the A inverse. It must be equal to the identity, which is equal to 1. When you multiply the inverse, you get back the identity. Same also, you do the left hand side, A inverse multiply A, you should get back identity also. What is the A inverse here? Okay. Is this 1 over A belongs to the set here?
Yes.
1 over A belongs to the real numbers except 0. If include 0, then how? If the set given are all the real numbers, can you find the inverse? Can?
No.
Can? No. Cannot, right? Okay. So if let's say the set given here does not say that non-zero real number, they only say real numbers, then in that case, your inverse cannot be found already, because you will have a case where 1 over 0 is not defined. So if they don't exclude the 0 here, the third condition cannot be fulfilled. Understand? So here they already exclude the 0. That's why 1 over A can be all the real numbers except this 0 only. So the inverse can be found in this case. So conclusion, you have fulfilled all these associative. This is associative, the first one. The second is the identity, so you get the identity is 1. And the third one is the inverse, so we can get all the 3 conditions to say that this is a group. So the set given, which is all the real numbers exclude 0 with the operator plus, is a group. So whenever the question asks you to determine a group, you need to show this one. You can see the marks allocated also. If the marks allocated is small, okay, you need to write all the 3 conditions. If they only give you 1 or 2 marks, and you can determine that one of the conditions cannot be fulfilled, then you write that particular condition is enough. But if let's say they give you 7 marks, 8 marks, that means you need to write all the 3 conditions. You cannot say that, oh, I cannot find the inverse. The inverse belongs to the real number is not exist. You just write 1 only like that, the one that is not fulfilled, then 7, 8 marks allocated, then you cannot get all that. That means you need to write out all the 3 conditions. Even the one fulfilled one, you also need to show. Okay? Now the next example, we have this exclusive OR. So this one, we want to show that it is a group also. And using the same method, this, because we have 2 elements in the set B, 0 and 1. So in order to show that the multiplication table, what do we want to show here? The answer for this? To show that it is associative, so we can get the answer from the table here. It is easier to show in the table. So 0 exclusive 0, what do you get? Remember this? Which one is 1? 0, 0 is? 0, right? 0, 1? 0, 1? 1? 1, 0? 1, 1? So if you go and do the associative, you can get the answer will be the same. For example, if I do the 0 exclusive or 1, exclusive or 1, and I do this first, and the answer I get is 1, 1, this is 0, right? The answer. And if I do this first, so this is also 0. Right? Meaning that no matter which part I do first for exclusive or this case, 0 and 1, I will get it is associative also. So here I only show you one. You cannot show like this. So you need to use a general form to show like this. A exclusive or B exclusive or C is equal to A exclusive or B exclusive of C, where all the A and B belongs to set B. ABC, not A and B, ABC. Okay? So your ABC will belong to 0 and 1 to show that it is associative. Now the second one, what is the identity? Can you give me the answer? Agree? All of you? 0 is the identity? How to determine? You see from the table here, you can see that 0 exclusive 0 is 0, right? 1 exclusive 0 is 1, right? So for identity, you should get get back the answer you have. Let's say 1 exclusive or the identity, you get back 1. So identity exclusive or 1, you get back 1. So here it should be 0. Yes. Same also for 0 lah. 0 exclusive or the identity, you get back 0. Identity exclusive or the 0, you get back 0. So here should be 0 also, right? So that's why the identity is 0. And you must make sure that it belongs to the set B. Now we have two elements here, 0 and 1. So what are the inverse for each of them? See? 0 inverse equal to? How to find the inverse of 0? Let's say I write like this, 0 exclusive or the inverse. Okay, inverse equal to the identity, which is 0. What is the inverse here? 1 exclusive or the inverse, you get back 0. Inverse exclusive or 0, get back 0. Inverse exclusive or 1, get back 0. What is the inverse for 0? exclusive what equal to 0?
0.
0, right? So the inverse of 0 is 0. Because 0 exclusive 0, you get back 0 here. Look at the table here. 0 exclusive 0, you get back 0. Here, this is the identity that we found just now, right? The 0 is the identity. This one also identity. So remember the inverse, we must get back the answer identity. Okay? Then only you determine what is the inverse here. Then look at the table here. 0 exclusive or 0, you get back 0, right? So the inverse is 0 lah. Okay? This one. Inverse exclusive or 0, get back 0. So inverse exclusive or 0, get back 0. So the inverse is 0 for 0. How about 1? What is the inverse of 1? 1 exclusive or the inverse, get back 0. So from the table here, 1 exclusive or which one get back 0? 1 exclusive or what equals to 0? So the inverse is? Can you understand or not? Can you see this table? So what is the answer for the inverse of 1? 1, huh? Okay. So for this one, you need to make sure that all of them must belong to the set B also. Okay? So both of them also inside the set B, which is 0 and 1. Huh? So next time when I ask you what is the inverse of 0, 0, then you need to know already. Huh? Next one. Now the theorem here is to show the sum of the inverse. They said that the inverse of any element in the group is unique, same like the identity. Once you get the inverse, it will be the same for the same operator and the same set given. Okay. For the cancellation law here, it means that you can cancel the A here, because both sides also you have A. This one also the same. BA equal to CA, so it is actually B equal to C only lah. We can cancel the A. Yeah? Then the inverse of A, if you do 2 times, then you will get back A. And for the AB inverse, it is B inverse, A inverse. Just like our matrix. Huh? When we have AB transpose, it is the same with B transpose, A transpose. Right? So these are some of the theorems. So the next part we will look at is the subgroup. Now, we already know how to determine it is a group. So, if let's say the set given are all the integers, now I take the subset of the integer and I want to determine whether the subset fulfill the condition for a group or not. So, to determine whether it is a subgroup or not. Okay. Now, the subset of G, this one, let's say you have the H, which is a subset of G, we call it as a subgroup if it fulfills these 3 conditions. Now, the 3 conditions for a subgroup, 2 of them are the same with the group, except the first one, which you need to determine whether it is clause under the operator given or not. So another way to say is the operator valid binary operation or not? So this is what you need to determine instead of associative. Just now, when we determine a group, we need to determine the operator is associative or not, right? But this one, to determine a subgroup, we only need to determine whether the operator is a valid binary operation or not. Do you still remember how to determine valid binary operation? If you have done your tutorial 4, the first question, then you should know already, right? Okay? How to determine it is a valid binary operation. So go back to your previous example, then you will know. So we look at the example here. Let's say now this G is a group, because we have proved in the previous example the set of integer with the operator plus is a group. It is associative, the identity is 0, and we can find the inverse is this negative A, right? So for the subset of this G, let's say we take even integer. Even integer, they are all the subset of integer, right? 2, 4, 6, 8, 10 is the subset to the integer, correct? Right? So H now is the subset of G. Okay? So in order to determine whether the H subset of G is a subgroup or not, so the first thing you need to determine is, if I take any two even integers with the operator plus, will the answer be even or not also? Any two even integer add up together, is it also even? 2 plus 4, is it even? Yes. 4 plus 6, is it even? Yes, right? But how to show? How to show any two even also even? We cannot use example like this, as I told you before, right? So how do we want to write the number is even in terms of a general format? Who knows? Who know how to write the even number?
The remainder after the division with 2 was equal to 0.
Divisor with? Divide with what?
Divide with 2 and
2? 2, is it?
Maybe?
Because if even number, as long as you multiply with 2, any integer, you will get even, right?
Yes.
Correct? 2 multiply any integer, you will get even. Agree?
Yeah.
Okay. So now, we let the two even integer, A and B, belong to the set H first. Set H is a even integer set. Let's say we have two even integer A and B. Then when you want to write it in terms of even integer, you can say that A equal to 2m and the B will be equal to 2n. What is the m and n? Chocolate. So the m and n belongs to the integer. It can be any integer as long as you multiply with 2, you get back even. Right? Okay. So what we want to determine now is, if I add up these two, what will I get the answer? Will I get even or not? So 2m plus 2n is actually equal to 2 times n plus n, right? So from here, 2 multiply any integer, m plus n will be any integer, correct? So when you get the 2 multiply any integer, of course you will get back even. So this is how you show the plus is a valid binary operation, because after the two integers, the answer you also get from the set H. Now is the set H, which is the subset of G. Okay, the next condition to find the identity. What is the identity for additive operator? Plus, now is plus. So you can say the additive identity equal to plus, what is the identity? 0. So is this belongs to even number or not? Is 0 belongs to the set H? Yes or no? Is 0 even number? Can 0 divided by 2? Can? Okay, so 0 belongs to even number. You must make sure the identity you found, it must be from the set given also. Okay, even is also, 0 is also even integer. What is the inverse? Let's say I find the answer for 2m. Because just now I already defined my A is 2m. So now I want to find what is the inverse for 2m. 2m inverse is multiply negative m, right? What is the inverse of 2m? The 2m, if you want to find the inverse, you must get back the identity 0, right? So the inverse here must be negative 2m. Alright? So if this is negative 2m, it's actually the same with 2 multiply negative m, right? Why I want to write like this? Because I want to show that this is also the even integer. I want to show that the inverse also belongs to h. To multiply any integer, you also get back even integer. So that's why I put it in this form, rather than I put a negative 2m. So 3 conditions also fulfilled. Conclusion: H is a subgroup of G. So the 3 conditions for a subgroup, repeat. The first one, you must show that the operator after the 2 elements, you get back the same set given, which is a valid binary operation. The second one, the identity also must belong to the set given, which is even integer here. And the third one, if you found the inverse element also must belong to the even integer. So here you have the 3 conditions to show that it is a subgroup of G. Okay, understand? Okay, this one, the next one is, let's say I have another subset. The first subset is the even integer. Now let's say I have the second subset, which is odd integer. What do you think if now I have the set of odd integers? Will I get back the same result as this? Do you think the set of odd integer also a subgroup?
No.
No? Which condition condition cannot be fulfilled? Identity. What is the identity for odd integer?
Also, the 0 doesn't belong to odd.
Okay, so you can say that the identity is 0, but 0 is not belongs to the odd integer, right? That is 1. How about the first condition? Can it be fulfilled or not? Any two odd integer add up together, do you get back odd integer? Odd plus odd, what do you get? 1 plus 3, you get 4. Is this odd? No, right? Okay, so the first condition also cannot be fulfilled. Huh? So we can just put the example like this, because this is also already show that it is not odd integer, right? So to show that it is not correct, you can use the example, no problem. Then you just show like this. 1 and 3 belongs to the H2, which is odd integers. So when I add up 1 plus 3, I get back 4, which is not belongs to H2. Identity is 0, which is not belongs to H2. Inverse, what is the inverse of? Inverse can be fulfilled because the inverse, let's say I have 3, then the inverse will be negative 3, right? If I have 7, then the inverse will be, what is the inverse of 7? 7 plus the inverse equal to 0. Inverse of 7 is? Negative 7, right? Negative 7 is odd or not? Odd or not? Odd, right? So that means the inverse can fulfill. H2 lah, don't write it is. So we just write H2 is not a subgroup of G. For the product of groups, you have these two groups. Let's say now we have two groups. We want to combine the two together. So what we do is we just combine their elements. From each elements, combine it together. Okay. So this is from G1 group 1, G2 group 2. So you just combine the two. And for this also the same. If you have the operator, binary operation for the combination of the two groups. So G1, G2, H1, H2, so we will combine it becomes G1, H1, G2, H2. Just combine the elements from each group. So look at the example 20 here. If you have the same set B, 0, 1, exclusive OR, so we have defined that this is a group already in our previous example. The product of the BN, meaning that if you have 0 and 1, you want to combine the elements from the table just now. Let's say we have this. So if I want to combine these two together, okay, Bn, meaning that I can have 2 bits, I can have 3 bits, 4 bits, and so on. So if I combine these two together, I can have 0, 0, 0, 1, 1, 0, and 1, 1, right? So that is for 2 bits. If the n is 2. Then, if the binary operation now is exclusive OR, so what you can write is from the first set, you have A1, you have A2, A3, and so on, until AN. Then exclusive OR with the second set, B1, B2, B3, until Bn. So if you want to combine them using exclusive OR, then the first element exclusive OR with the first element, second element exclusive OR with the second element, and so on. Just do it like this, okay, using the operator given. So sometimes, because this is the 0, 1, right? So sometimes we don't put the comma. Sometimes we just write 0, 0, 0, 1 like that, so without the comma. Now we look at the example for 2 bits B2. If let's say we only have n equal to 2, then we can put it in a table like this. Combine the 0 and 1 for 2 bits, so you have 0, 0, 0, 1, 1, 0, 1, 1 using exclusive OR. That means the first element exclusive OR the first element. So we have 0 exclusive OR 0, we get 0, second element also 0, right? This one, the first element is 0, second element is, what is the second element?
1.
1. Okay, this is 1, this is 0, and then this is 1,
1.
1. Yeah. Can you fill in all? Second row, this is 0, 1, this one,
0, 0,
0, 0, third one,
1,
1, 1, fourth,
1, 0,
1, 0, third row, 1, 0, second, 1, 1, third,
0, 0,
0, 0, and fourth,
0, 1.
0, 1. Okay, fourth row, 1, 1, this one, 1, 0, this one, 0, 1, 0, 0. Okay? What is the identity here? What is the identity?
Zero.
Yes? Just now for 1 bit only, their identity is 0, right? Now 2 bits. Identity is? If you want to determine 1 by 1, you can do so. Just take the element 0, 0, exclusive or identity, you get back 0, 0. Okay? Then if you take the second element 0, 1, exclusive all the identity, you get back 0, 1. Third one, 1, 0, exclusive all the identity, get back 1, 0. What is the identity here? Yes? Identity equal to 0, 0, right? Okay, 0, 0, Now, find the inverse for every element. So we will find the same like this. You will have 0, 0 inverse equal to 0, 0, 0, 1 inverse equal to 0, 1, 1, 0 inverse equal to 1, 0, and 1, 1 inverse equal to 1, 1. You will get all these are the inverse for each of the elements here, because when you find the inverse, you will get back identity 0, 0. Okay? Have a break now, then we will continue the last part of this chapter.